Thanks for your time today and your interest in Attestation. This is part 1 of Attestation Secure Boot using our ECC608A. This presentation covers a few secure boot methodologies using this device. Secure Boot, as well as Secure Download Firmware Upgrade, better known as Secure DFU, fall under the category of attestation. Attestation is the affirmation that something is correct, true, or genuine. Secure Boot assures only genuine code is executed on startup of the system. Secure DFU would assure the code being sent to the system is truly genuine and comes from a known good source. There can also be runtime attestation. This is where the code is checked on the fly while the system is operating to make sure no code was tampered with. Local attestation could be programmed as a periodic check of the code. A bit more secure than that would be remote attestation, where a remote authority asks for a particular section of code to be hashed, possibly signed, and sent back for authentication. This presentation covers Secure Boot only. Please see part 2 of this presentation for the description of Secure DFU. Let's first consider asymmetrically authenticated Secure Boot sequence. This will be accomplished by verifying the digital signature of the application image. This signature was provided by the OEM using the OEM private key. This is an extremely secure method, which is ill-suited for execution by the firmware of an MCU, especially a lower performance MCU. There is a significant burden in code size as well as execution time for elliptic curve mathematics. Coding these crypto primitives in the bootloader could easily cause the code to outsize the bootloader. Not to mention the need to secure the OEM public key. But let's talk about the needs of the public key in just a minute. What I want to say now is Microchip's crypto devices offers hardware acceleration for elliptic curve mathematics, with an ECDSA verify occurring in only about 50 milliseconds. Code size is also significantly reduced to a simple API call. We start off in this condition. Programmed into the MCU is a bootloader. This bootloader drives the entire process. Also programmed into the MCU is the application image. And finally, we have a signature of the application image stored as well. The signature is the result of an ECDSA sign operation on the hash of the application image. The sequence of the operation is as follows. The application image is hashed, creating a digest. In some cases where we need to limit time spent in boot, this digest is sometimes pre-stored in flash, so it's immediately available. Best practices would suggest that we hash the entire AI every time we boot. I often say there's no perfect security. Security is a hurdle, which we just make higher than our adversaries will jump. You need to decide how high they'll jump and adjust accordingly. This digest, along with the stored application image signature, are sent to the crypto element for verification. The signature of the AI digest and the OEM public key are fed into an ECDSA verify function. Now let's get back to what I started to say about the public key. Public keys are not secret. They're open to everyone. But the OEM public key needs to be secured, therefore trusted, as it is the basis for this signature verification. If an adversary has the ability to change this public key, any security has been completely compromised. So in this particular case, even though public keys are not secrets, this one needs to be secured. It's still not a secret. Anyone can know it. It just needs to be protected from being overwritten. And while we're discussing this public key, let me also say we probably don't want to use the OEM's root private key for this signature. Following best cryptographic practices, keys should be reserved for one purpose and not reused for any others. The proper thing to do would be to use an OEM intermediate key to sign the application image. A certificate from the OEM root would be needed to assure the validity of the OEM intermediate public key. I feared showing that level of detail in this presentation might do more to confuse than enlighten, so please forgive me for implying we should use the OEM private key for signing application images. It could be done, but again, best practices advise against it. Symmetric cryptography can be used for secure boot as well. We start out similarly to the last slide. We don't need the signature anymore, of course. The sequence of the operation is as follows. The application image is hashed, creating a digest. Again, in some cases where we need to limit time spent in boot, this digest could be pre-stored in flash. A random number is generated in the crypto element and sent to the MCU. The application image digest and this random number are hashed to create a message authentication code, a MAC, which is sent to the crypto element. This randomness thwarts any attempts at replay attacks, which would be recording a previous successful authentication and trying to feed that back into the crypto element. The random number makes every authentication unique. A copy of the genuine AI digest created by the OEM and stored in the crypto element is used along with the random number to check the MAC coming from the MCU. This is about the time someone asks about an adversary probing the I2C line. We'll talk about this in the next few slides. When an adversary has physical possession of your device, unlimited resources, and is highly motivated to crack your security, I'm not going to mince words here. You're in real trouble. But we don't have to just roll over. We can make that hurdle I talked about earlier quite high. And we can make sure any successful hack will impact only that one physical device and not compromise your entire ecosystem. We can confuse things further and even obfuscate the I2C bus using what we call an I/O protection secret. This is a secret which is not transmitted during normal operation. Let's go back to manufacturing. Usually, manufacturers use some kind of diagnostic code on newly created boards to make sure they are created properly and everything works. This diagnostic routine is then overwritten by the production application image. During that manufacturing cycle, in the relative security of the manufacturing line, this diagnostic code should ask the crypto element to create a unique random number to be used as the I/O protection secret for this particular microcontroller/crypto element pairing. This number is stored in both the crypto element and the microcontroller. It is unique to each PCB. If anyone were to decapsulate the micro and find this secret, the hack would only impact this one board because all the rest of the boards would have their own unique I/O protection secret. They would remain uncompromised. Let's look at a couple of ways this I/O protection secret can be used. Let's revisit the symmetric secure boot sequence and add the I/O protection secret. We create the AI digest as we did before. We also create the random number in the crypto element and send it to the MCU as we did before. But this time, we also feed the I/O protection secret into the hash function. The crypto element reproduces the MAC using the random number, the known good AI digest, remember, from the OEM, and the I/O protection secret. The result is compared for authentication. Even though an adversary might know the real AI digest and read the random number, with no knowledge of the I/O protection secret, it is infeasible to guess the MAC. Now let's see how we can use the I/O protection secret to hide that random number or anything else we want to obfuscate when it rides across the I2C bus. We can use the I/O protection secret to obfuscate the I2C bus when sending a secret across. The method is quite simple. Let's imagine we ask the crypto element to create an encryption session key. This could be the result of key derivation function, Diffie-Hellman, etc. That secret is first exclusive ORed with the I/O protection secret inside the crypto element. It is then sent across the I2C bus, obfuscated, of course, to the microcontroller. When the microcontroller receives the obfuscated secret, it exclusive ORs it with the I/O protection secret again, thereby revealing the original secret sent. We need to talk about one more thing. As we know, the crypto element is inherently secure, but not so much the microcontroller. It is still possible for a hacker to literally take the entire microcontroller off, put a new microcontroller with code rendering the crypto element irrelevant. We are able to limit hacks to a single device in physical possession of the hacker, but still, we want to make sure life is as difficult as possible for hackers. We can add more height to that security hurdle I talked about before by locking the keys and credentials needed for cloud service access in the crypto element and only allow them to be unlocked after a successful authentication. In this way, we can force the use of the crypto element. I want to thank you for your time today. If you have any questions, please reach out to your local Microchip technical support professional. Thanks again.